Everybody for joining our March ECSS symposium. You have to excuse the sound of freedom noise in the background here. We're near a Air Force base, or I guess it's a Marine Corps. So our first speaker today is Dongju Choi from SDSC, and DJ's been involved in the work with our School of Medicine here for quite some time on the use of GPU-based applications for radiation treatment planning. And DJ's work caught my eye. He was giving a tutorial here, so I kind of keep a lookout not only for projects that are finishing up in ECSS, but also for tutorial work that folks do. We have a number of folks involved there. So with that, I will let DJ take it over.
Thanks, Nancy. My name is Dongju Choi. People know me as DJ. Today, I have a slide with some GPU application that we developed in Radiation Oncology Department at UCSD. These tools are some of many tools that we in oncology department to use the cancer treatment. We've been Amit and I've been involved in this project for 2 years to help this tools to speed up so can be used better for the patient treatment. The funding that supported our work was support the oncology department is UC lab that we got 2 years ago, and it's still going and almost ending. Here, some of the flow charts that the radiation treatment conventionally was working. The top one is the conventional one, and the low bottom one is the one we want. So if we see the conventional one currently used is this way. First, the patients come with a tumor, and so the department, radiation department, take CT scans and see where the tumor is and how is it going to be, and with a numerical simulation. And after that, it is so slow, the tools are so slow, so you cannot do it in real time in 1 day. So a few days later, the simulation output is handed to the doctor, oncologist doctor, and the doctor plans where to shoot the radiation to reduce the tumors. So he has to do the radiation treatment design, and some of the this treatment design has to coordinate with the radiation equipment, which has photon or electron or other way of radiation source, and some practical configuration. So that configuration was the source has to be optimized, and finally the dose, the radiation dose on patient's body has to be calculated to make sure it matches with the patient's treatment design that doctor wanted originally. And also that the process and tools are very slow currently using the machines, poor machines. And then after a few days, we call the patient back. Now our planning is thoroughly done, and the patient is lying on the bed and wait for the treatment. The treatment is not just a one-time radiation exposure. It has to be repeated several times. And if you see this repetition tools, you don't have any feedback routines how the tumor is shot with the source, or how the tumor on the doctor on the day of the arrival is changed. Or those things are not considered because of the slow tool response time. So we assume everything is the same, and we just keep repeatedly treating the patient. That one has to be changed. In this online art, which is adaptive radiation, what we want is we want to put replanning in these repeat feedback routines. We want to treat the patient, and then we want to see the patient, even simulate the patients again, and even plan that again with the doctor's involvement at the site of the patient's visit. So we can give a better treatment even in this loop. To do that, we have to accelerate the tools that we have before. Even if we can accelerate the simulation tools or planning tools, we can save lots of time for the patients, not just waiting days for the patient's tumor to be simulated or planned or stuff like that. We can accelerate the treatment process much faster. To do that, the tool algorithm is there. Not much changing. To accelerate it, we have to parallelize the tools. You can parallelize using existing cluster tools, CPU cluster tools, or you can use GPU. We started to look at the CPU clusters in the beginning, but at the same time, GPU hardware came. So we decided to look at both of them and see which one might be a better fit for us. And this slide will talk about the GPU side that we developed, and was found out to be quite successful for the condition of hospital situation. In the hospital, the cluster is a little bit over budget, or system maintenance is not much a focus for them, or we thought about using some on-demand type of resource scheduling with other supercomputer centers, but latencies and some reliability is an important issue. So considering all these things, if you can get a similar performance, GPU was sort of a very attractive tool because you can have one or two workstations inside the treatment room and get similar parallel performances there.
DJ?
Yes.
I don't think you're advancing the slides on the web conference.
Oh, I'm still on the first slide. Sorry.
Oh, okay. That's what I was thinking.
Okay. Oh, yeah, I'll go faster.
No. It's just fine. It's a lot of good background. Thank you very much.
Okay, sure. Okay. Yeah, I'll go a little faster. Okay, here we go. Yeah, so the fundamental difference here, CPU and GPU in this slide, what the relationship of the CPU and GPU here. CPU is currently, not the microprocessors, but currently lesser cores. GPU has lots of cores, 200, 400, 500 even now. And the CPU has large caches. GPU, older generation didn't have a cache, now it has caches. It uses both DRAMs. And the GPU cannot stand alone. It has to survive or operated by CPU guys through the PCIe, very thin bandwidth. That was the problem. Okay, because GPU has to be controlled by CPU with a small, very thin memory bandwidth. I think currently microprocessor same way. So that was one of the weak points in the GPU. And another biggest weak point is GPU doesn't have much intelligence. I can say compared to the CPUs, you have to be strictly SIMD parallelized, or you lose great performances to coordinate all these 500 cores, or at least you have to follow the unit SIMD parallelization, which is GPU guys called warp size. Okay, so let's look at the simple application that we tried 2 years ago, that using GPU or MPI. Here, just GPU side. One of the applications we frequently use in radiation department is it's more like X-rays, but X-rays, but applied on the CT. It's a three-dimensional X-rays or three-dimensional volume that you can find. Here, this rectangular box is a patient. Patient is lying down, and the source photon is going through, or X-ray is going through. Then you can see the projected image on the bottom here. The two-dimensional image here is it can be chest images or any body images two-dimensionally. You can that point in the volume is called the voxel, we call it, and the point in the two-dimensional is, as you know, we call it a pixel. Okay, so to make this two-dimensional image, you have to have many X-rays pass through the body. Many X-rays pass through the body. You can calculate, if you have a CT volume already, then you can calculate these images just doing the ray tracing in the computer science algorithm. You can calculate the X-ray images or 2D images here. So to shoot many rays is we call it ray tracing. We can do the ray tracing on the GPU to have that each ray as one thread. Just to follow the ray where the body is intersected. Whenever the body intersected or go through the density or the point, the material property, you add it up and then project it on the target images. So this one is a very embarrassing parallel, and which was a perfect application for using GPU. Of course, you do the same with the MPI. This is just many nodes to do the similar parallel performances. Compared to one GPU, we got good, impressive performance in the GPU application, developed the GPU application. Okay. Of course, yeah. Here, that in the GPU application, we could use a special texture memory in the GPU, and the three-dimensional texture memory was still stored in the stored for the CT volume, and we could take advantage of some NVIDIA three-dimensional interpolation, hardware interpolation scheme, which we should have done in the software-wise in other products. We could take advantage of some of the stuff that GPU currently NVIDIA CUDA was providing. And so the CPU version in this case took like 3, 4, 5 seconds for the same size of CT voxel to pixel size. Now in the GPU version running on C1060, the older generation of GPU, now it takes like 20, 30 milliseconds. So we get close to 15 times speed up compared to Nahellam core. This one just used just one core, not multiple cores, because it was just multiple cores. We didn't try OpenMP or MPI. We tried that, but we needed more nodes to get comparable performance. I don't remember what that was. Okay.
EJ, this is Ralph. How do you do? I mean, presumably, as the beam passes through different kinds of tissues, the scattering will be different. And so, how do you do the SIMD stuff if it's sometimes going through bone and sometimes going through tissue and whatever.
Yeah, the scattering was not considered. It was just the one passing through directly. That is later you can see the scattering. All those things are considered in some either hybrid DRR to Monte Carlos or Monte Carlos. But here, just it was a pure one ray without any scattering.
I see. Okay, thank you.
Sure.
DJ, there was one more question from the audience. What the goal for the turnaround time was between simulation and treatment, when you said that simulation can kind of speed up the analysis time of the images. What was yeah, go ahead.
Yeah, that's very good. The goal was not just one application performances, but here the target is we want to make sure this one is in real time, almost real time, not real time. The patient is on the bed, and we don't want the patient to wait like 10 minutes, 30 minutes. We want to make this thing like within patients. So maybe all tools involved in this repeated process less than 5 minutes. That was the goal. So we are trying to reduce all involved tools to be as fast as possible.
Thank you. That answers the question, sure. I think.
Okay. So we try to manage this DRR algorithm to run it in within less than 50 milliseconds. That helped us a lot instead of many seconds, because we have to do many operation of these things during the process. Okay. Now let's look at some of the tools that are involved in this replanning process. This is the replanning process is the one inside the feed loop that the patient is now on the bed. We have to use all these tools to make that treatment more feedback way. Okay, replanning way. So one of them is the CBCT, combined CT reconstruction, which is like here the difference between CT and combined CT is combined CT is much smaller and much faster and more coarse, but you cannot do the regular CTs when the patient is lie down and to evaluate where the new tumor is and stuff like that. You do a quick ad hoc combined CT, use the combined CT to calculate where the tumor is now, because the original plan was like at least a few days ago, then the tumor position might be different now, and then also where the patient is lying down might be not exactly the same as before. So we have to know how the tumor is reconfigured, and we have to match with the previous analysis. So this reconstruction is required inside the loop. And then we have to do the deformable image registration, which is like now tumor is, it was the same tumor, but days passed, and that patient's lying position is different. We have to know exactly where the previous tumor is now corresponding to the tumors today when the patient is on the bed. So we have to match that. That's image registration. And also the patient the tumor is a little bit different location. We have to recontour the doctor's planning. Doctor painted here the patient's target here before, but tumor is a little bit moved away because of repositioning. So we have to do the recontour plan the tumors on the new image, and then those has to be calculated on that thing, and we have to re-optimize for the new tumor positions. So several tools have to be considered for the GPU parallelization. Also, we tried some of them for the MPI parallelization. We just go strictly GPU parallelization with this slide. Okay. So image registration is called the Demon's algorithm. This one was the original image with the tumors, and this one is at the time of the patient's treatment, CBCT. The difference between CT was CBCT. CBCT is much simpler, concise, smaller. You can do it quickly when patients are treated on the same day. The algorithm is here is I0, the velocity on each pixels from here to here morphing is involved with I0, intensity of the original one, intensity of the later one. And then, so what we did is just each pixel we have to calculate this one. So what we did is each pixel is thread parallelized. And then the performance for this volume of CT size, we got almost 50 times again. And the GPU ran on C1060, and the CPU ran on the Nylam 1 core. Okay, and then next application is convex CT volume, CT volume reconstruction from many of these two-dimensional images. The image on two-dimensional image, relationship between two-dimensional image and then the light sources like this. F3 here is the patient's CT volume, which we want to calculate, and the DR is the line path here, and then the image on the 2D image is recalculated this way. F is CT volume. Here, next way, you will see that another variable called projection, which is projection operator to the CT volume gives you two-dimensional images. We have a bunch of two-dimensional images. We want to calculate the CT volume from this relationship. It involves this kind of steps of optimization, updating, and minimization, and correction. If it is some volume is calculated less than 0, it doesn't have a physical meaning, so we just set it 0. So we see three variables are involved in this calculation: the transient CT volume F, and the projection variable, and the two-dimensional images. So these three are juggled to be calculated through this step. Two-dimensional image is calculated the same way as we're doing ray tracing. So each ray to the CT volume is one thread. So it was picked like we did it on the DRR before. And then we have to calculate the transient F, which is a three-dimensional volume. Each volume box is one thread. So it has many more parallelization here, which it took quite a bit slow. But it was even much slow during the CPU times, which was not even doable within a day. And then we have to calculate this P matrix, which involves with this two-dimensional coordinate and the three-dimensional CT volumes. So we have to do the two kernels in the GPU side. First one do the two-dimensional thread parallelization, and the second three-dimensional voxel parallelization to calculate solve from this equation.
DJ, just a few minutes left, okay?
Okay. Okay. So using that formula, this is the ground truth of the reconstruction, and this is a poor method that we did before because we're so limited in the times. Now, using the new algorithm and using this GPU parallelization, we made almost close to ground truth output in quite a realistic time. Okay, so the recontour was quite pixel by pixel parallelization based. We could achieve that one. And then we have to calculate dose on the patient. There are two types of way calculating the doses. One is a pencil beam way. You make the cross profile of each beam. The beam is shooting down the patient this way. It will be 10 by 10 or 100 by 100 beams here. You can use the profiles to each beams and then calculate that way, or you can shoot millions of Monte Carlo histories and then see if any history passes through the patients and add up to the projected images. Each thread, for the Monte Carlo method, each history is calculated in one GPU thread. Compared to CPU times, the final version is like 50 times to 70 times faster on the compared to the Nylon to C1060. And the pencil size the beam model we parallelized on the voxel, and then this many beams and this many beamlets. Beamlets are the profile of the beams. Number profile of the beams. We get very similar to the Monte Carlo method, but we got some modified version, which is density corrected, which we corrected the profiles, and then we got much similar to the Monte Carlo method. The Monte Carlo method was previously sort of very close to the real simulation. Now the FSPB is much quicker, but is very close to simulation output. Okay, pass that one. Okay, so the FSPB is quite quick. It's everything is less than 1 second. Now we have to calculate the optimization. So there are three types of optimization: fluence map optimization, which means it just directly compare the intensity of the planned to the new optimization, and it has to match as the planned as doctors. The contour the contour has to be same. Two others are modified one. The DAO adds the first two FMO plus the source aperture. The source has the beam source has a multiple gates to make aperture, like a picture, the photo aperture. You have to. So this DAO considers aperture controls. VMAT model even considers this aperture and its intensities and the more realistic terms, how the beam is moving, how the aperture is. Those considering the speed and times and the realistic components is considered. The FMO model we parallelized on the box level those calculations. There has to be this has to be calculated a lot, so we parallelized and gave the speed up, and the result was here. So patient's contour history here. This patient's histogram shows it is the optimization really gives a good those objects and saved many other vital organs. Speed up is quite impressive here. It takes now 0.0205 2 seconds. It used to take like minutes before. And so this is a VMAT case. The VMAT case is a solid line, and IMRT, which is the one previous before the FMO, which is the same as and you can see the vital organs are much more saved. This solid line is much lower than this dashed line of FMO. So because we consider the apertures, that we get better objectivity. Okay, I think that was the end of my talk. In summary, we have developed GPU-based computational tools for real-time treatment planning. So far, luckily, I think most conventional problem size have been well fit to one GPU hardware, so we could just had one GPU parallel programming, not mixing other programs. But to get to become more ambitious, to have a final resolution and a more faster way of process, we definitely need to add multiple GPUs and mixing the multiple GPUs and CPUs, and that requires to be hybrid programming, hybrid parallel programming. So for typical prostate cases, the achievement is second for the FSPV calculation, 40 seconds for the Monte Carlo. Monte Carlo doesn't have to be involved in repeated processor because the correct FSPV now shows very impressive realistic output simulation. Optimization also takes less than 1 second or 2 seconds, or even the highest realistic calculation 30 seconds. Now it all involves, all these things adds up to make favorable for us to do the real-time adaptive treatment therapies. In the next step, we will do the multiple GPUs, larger problems, final problems, algorithm improvement. We will do also now. Everything is becoming dynamic. All tools are becoming dynamic, and more calculation, more process has to be done. So software integration, scheduling framework, all these things, new problems are coming now. Currently, all these tools are only research tools. We soon want to do a clinical implementation and evaluation. That's it.
DJ, thank you very much. That was a terrific talk. I really wish we had more than the 20, 30 minutes that we have for it. It was very interesting. We have at least one participant on the phone lines who's seen this from the patient perspective and had the calculations done on a Spark 10, so they're definitely interested to see how things have improved over the years. I was going to ask you about, the phone lines are open, so I'll let other folks ask questions while I'm uploading Tom's slides. But I was going to ask about sort of the checkout involved to be able to use this in actual clinical settings. And I think you addressed this a little bit at the end when you said this was a research tool at the moment, but not used on actual patients. I mean, I think there's a tremendous argument for, moving that forward, especially when you look at the, the dosages and the reduced dosages that you can use and still have an impact on the tumor.
Yes, yeah. So I think there is lots of rules and laws and to be realistically applied this to the real patient. I think it is not just a simple desire you can do. You have to prove this is really solid to any related involved institution that this will be beneficial. Then we can get the green light to work with the clinical implementation stuff. Yeah, not just reduce the time during the process of this development. We realized that some of the smart algorithms, smart parallelization can even reduce the unbeneficial dose to the patients. Yeah, there was a sort of a surprising found so that so we can benefit the patient in just a quick treatment way, but also we can we can benefit the patient in less harming. Yeah.
One more question for DJ, and then his contact information is on the symposium website. The slides will be up there too, as well as a recording of this if you want to ask some questions later. But